Welcome to Chapter 6, Part 2. We left off at mesh network topology, and now we're going to move into some major networking concepts. So, we're going to take a bit of a deep dive into kind of the five major networking concepts for data information systems, and let's just get right into it. So, beginning with protocols, let's talk about what a protocol is. In other industries, um, that there are protocols, but when there are kind of a rule set agreed upon by a lot of different manufacturers, we call those standards, and in this case, we call them protocols. So, what are protocols? There's some agreed upon methods. That's pretty obvious there. And what they do is that they allow different organizations, manufacturers, companies, firms to rely on a certain set of rules to do data communication. Okay. And specifically here, we're talking about some hardware rules, some different data information packet rules, and a packet is just a small bit of information. And protocols, we use these rules to build up higher level types of communications and interactions. So we know what protocols are. Let's look at two. Well, it's actually one, but it's actually two protocols together, and it's called TCP IP. And we group these two together, but it's two protocols that pretty much the internet is built on. It's kind of an industry standard suite or group of protocols. And to think about it, the TCP is Transfer Control Protocol. So this works on kind of the transport layer. We talked about layers a little bit. It allows us to establish links between computers. It makes sure that the information that we're sending uh, is received and is the integrity is still intact, and also regulates the flow of data. Okay, now that is transmission control. We also have another one called internet protocol, which pretty much operates at the network level. So if you think about it, the transmission is just point to point, but you can't get from one point to another point unless you have a network, and that's what this protocol does. And it allows us to break information into small parts that we call packets, and we can break those two parts into the network address and the node address. And this is where the magic happens because regardless of which topology you're using, you're going to have a network address on that topology, and you're going to have a node within that topology. And with those two pieces of information, we can attach those to some information content, the information that we're interested in sending. And using this protocol, we can get it there. Now, speaking of getting it there, anytime you want to send something from one place to another place, you have to have a route. This is true for data communication systems. And of course, we just call it routing. Now, within routing, we can break up some important things. The first thing is a packet. We talked about what a packet is, which is kind of this binary data that we send from one computer to another. But then we have to determine how to get it from one node to another node. And that involves the process of deliberating a path, finding a path. And we call that routing. And this is determined by the type of network that we're using and the software we're using to do the route. And to go a little deeper, when we're making this decision about how to select a route, we have a couple different options. We have centralized routing, where one node is in charge of selecting all packets. And this should sound very familiar to when we were talking about the network topologies, because if you have a centralized topology, you're then going to have centralized routing. And then, of course, the inverse of that is if you have a distributed network, you'll have distributed routing. Now, what does that mean? In a centralized routing, one machine calculates the entire path and then sends that packet on its way. In distributed, one node, and I said machine earlier, but it's a node, one node just calculates how to get to the next node. And then that node picks it up and does that calculation to get to the next node until it eventually reaches the end destination. Now, to do this, we use a routing table, and this is generated by software. And in essence, it just tells us where all the different nodes are and allows us to determine the best possible route for a packet. To dive a little deeper, we can use routers. So not only do we do the routing, but we can have specific devices or machines just for doing this task. You probably have a router at your home or wherever you hang your hat that does this for you, and it probably has a Wi-Fi signal. It's probably a Wi-Fi router, and this is exactly what it does. It's a machine. It connects to a network. It chooses the best path for packets and sends it on its way. And then the hope is that if this thing is engineered intelligently, it should also prevent network jams and be able to handle different types of packet sizes. So you can see we're taking just simple individual protocols and stacking them layer on top of layer until we can get to something complex that can handle a lot of stuff for us. Now, there are different types of routers, okay? There are static routers, which require kind of the network manager to tell it where everything is. It is set up in advance. And then there are also dynamic routers. And a dynamic router will build this routing table on the fly every time that it needs to kind of do this. So you can see the difference there. You probably have heard these terms before when talking about IP addresses. Back in the days of dial-up, and dial-up is where we use the phone line. Every time you would get on the internet, you would get a new IP address. Okay, and that IP address was considered dynamic. And the reason it was dynamic is because you never knew what the IP address would be the next time. You could predict what range it might fall in, but you wouldn't know exactly what your IP address would be every time you'd log onto the internet. What that does is it means that you can't give your IP address to a friend on Monday and expect them to be able to connect to your computer again on Wednesday directly with that IP address. So a dynamic table would, you know, redo those calculations every time you wanted to connect to the internet versus a static router, which most cable modems are kind of fall in this category. You get one network address and you keep it the entire time you have a contract with kind of that internet service provider. So the static, the ISP gives out the information the static router is going to use, and it just uses this information for all of its processing. Okay. Now that dynamic we just talked about, kind of an ISP and a an individual end user, we have kind of a client server. We're the client, we're purchasing service, and then or we're using service, and the server is delivering service. Well, that model is also in effect when it comes to uh, communication systems. And to break it out for you, a client server model, in essence, is software is ran on a local computer and it communicates with a remote computer. The server is remote, okay? And then the local uh, machine is the client. Now, why would we do this? Well, the thing that makes this really good is that we can scale it. Instead of having a 1-to-1 ratio where each computer has to have kind of its mirror on the other end, we can make a very well built out server that can then communicate with less expensive, less costly clients. So when we're communicating on a network with a remote server, we can scale this pretty well. And to kind of understand the different levels of logic that goes into a client and a server, we can look at the different things that we do with it. One, we present data to a client. Okay, so we call that the presentation level, and that's where the client makes a request and we send it out to them. Okay, now that request is at the application level. So presentation is kind of what's returned to the client. Application is a request that we can take from the client. Okay. And before we can process a request to present it to them, we have to have a data management level where we actually kind of translate that request into something that's meaningful and then collect the data, do the storage and appropriate operations on the server end, respond to that application request, and then present that to the client. And This sometimes is referred to as a two-tier architecture, which means the client communicates with the server. Well, I apologize. The other thing is a two-tier architecture. Client communicates directly with the server, and it kind of works in small work groups as opposed to this big, um, kind of this big infrastructure. Two tiers a little bit smaller, closer, more tightly aligned, and this is a little bit quicker. So instead of going to the cloud with just a regular client server, we can also do a two-tier where we're a little bit closer and things are controlled much better. Now, some of the problems with this is that it requires you to do a lot of modifications when you want to make changes because it's not as built out and robust as just a generic client server model. Okay. And here is a bit of a kind of a description of what we got, a two-tier, where we've got the server who's working with the clients on one tier and then working with the data layer, the data management layer here. So here's our presentation layer here with the clients. Here's our application layer with the server. And then here is our data management layer. Okay. So in a two-tier architecture, this is pretty tight, pretty close. A lot of different websites kind of run this type of model, but two, meaning that we only have two tiers outside of the server, can be expanded to an N tier. An N is kind of mathematical for any number tier of architecture. And the way we do this is first we have to balance the workload. So we can't have it all concentrated in the server here if we don't know how many of these different client tiers we're going to have. We're going to have to distribute some of this work. You know, now, what's the advantage of this? Well, it could be three-tier, it could be four-tier. We're going to get better network performance if the work is distributed in other places. The problem is if work is distributed, it means there needs to be more communication and there's going to be more network traffic. And then finally, there's a lot of places for things to go wrong. Maintaining 5 servers is going to introduce a lot more opportunities for bugs and glitches than maintaining 1 server. And you can see that here in this kind of diagram of an N tier. So what have we done? We still have our data management layer here, okay? And then we even have kind of in the data tier this vendor system. And then we have an application tier here. So we still have those 2 layers. Now what we have done is we have kind of split out the presentation tier and the application tier and introduced a level here that is a little bit of both, that is focused on presentation. So it's a web server, but still communicates with the application level. So, this is how our bigger things are probably set up and structured similar to this. And what does this require? Well, all these application servers now have to communicate with one another. So if they're communicating with one another, we are going to have more network traffic between the presentation tier and the data tier than we had when there was just a single server. But, if we configure it properly, we'll then be able to get some economies of scale here. If 4 requests come in, each one can take an application request as opposed to the web server doing each of the 4 in order. So we do have some advantages here. And I think the book does a pretty good job of getting into that. Now, to contrast an N tier with just a 3-tier system, we'll see another example where we have this level here, the clients, we're going to call that the presentation level, the application level, and the data level. So you can see there's a bit of a difference here. It's good to understand what's happening in these videos, not in this video, in these 2 diagrams, because it's going to help solidify the different layers that these data communication systems are built on. It's not just one thing does everything. It's each layer plays a role that builds up to kind of an end product. So let's switch gears a little bit. Let's talk about networks from a more broader perspective, more on the actual medium in which the network works. And what we're talking about here first are wireless and mobile networks. Wireless, obvious what wireless is. It's no wires. And then we have different types of wireless networks. We have wireless that we consider, generic Wi-Fi. Then we also have mobile networks, which are radio frequencies, which, big cell towers, and they have base stations to communicate these large batches of signal. So, what are some advantages and disadvantages of this wireless approach? Well, the advantages are very big advantages. A, mobility. You cannot have a cell phone, you cannot have a smartphone without a wireless network. The idea that you would have 7 miles of cord that you walk around the city with connected to your phone is ridiculous. So mobility and flexibility. If you can take something somewhere, you can do work in places you could not do it with with a wired network. It's easy, ease of installation, of course, because you're not running cables, and it's relatively cheap. Now, the disadvantage is a big disadvantage, and it is throughput. And we've looked at throughput and called it many different ways. We've called it bandwidth. We've called it, you know, just generic speed. But this is a big disadvantage of mobile, or wireless, especially when we're talking about data communications. It would be very difficult to administer a database from your smartphone if you live in a remote, non well built out area of wireless technology. Excuse me. So, with those things said, wireless has some very good advantages in terms of mobility and flexibility, but it does have some disadvantages as well. Throughput being the biggest, limited range, and then the things that we need to worry about when we're talking about systems that are very, very sensitive is security. Because, think about it. When you send out a wireless signal, your phone is emitting that signal in every direction. So if I am a hacker, I do not have to get physical control over your device to be able to capture the data which you're transmitting. And as long as your device believes it's communicating with the server, it will keep transmitting in 360 degrees. So, if we take a clock and use some military terminology, if your server that you're communicating with is at 3 o'clock, but there's a hacker at 9 o'clock, that signal is going to both. And that's a major disadvantage of the wireless and mobile networks. Now, we can take care of this with some security and some protocols that allow you to safely use these networks. But just as we've already noted, it's an arms race here. And as security gets better, hacking methods get better. So wireless does have an innate flaw in terms of frequency and broadcasting information. Okay, how do we categorize these? We have wireless LANs, which are similar to a wired LAN. The wireless network in your house is probably a wireless LAN, and then the wireless WAN, which would be city-wide, or well, there may be statewide wireless. I haven't really seen it, but citywide wireless is a really good example of this. In Bowling Green, there's a wireless network. Another big wireless WAN would be WKU's wireless network if you happen to be on campus. So, what are the differences here? One versus the other. A wireless LAN is about 100 meters. In my in my experience, you're lucky to get 100 meters out of a wireless router. Wireless WAN, much broader range, regional, nationwide. I guess a wireless WAN, a big one would be Verizon. So if we think about the carriers, there we go. Those are huge WAN networks. Speed on wireless LANs is typically faster than you would get on a wireless WAN, just because since the distance we're covering is a lot smaller. With some of these new standards, we don't have it on here, but 802.11ac can transmit up to 500 or 600 megabits a second, versus a lot of the WANs are still in the double digit megabits. And that's why your LTE service is never really as fast as your Wi-Fi. And then data security for the LANs, it's pretty much basic data security. Now, for the wireless WANs, a lot of times you can get a lot more well-built security protocols in place. Now, at this data security level, you as a user can increase the data security on your particular network, irrespective of how it ships from the device owner. And that's where our security experts in business come in, because you want to make sure you are employing someone who understands data security and has a good eye on what is important to keep your network secure. Now let's look a little bit at mobile networks. Most mobile networks consist of about a three-part architecture. We've got base stations. These are the broadcasting components of the network. We've got mobile telephones, switching offices. So, these are kind of the switchers. These are the people who are interacting with the user. And then we have subscribers, and that's kind of the end user. Something for you to study for the test. I'm going to leave time division multiple access up to you, okay? And that's two. There's time division, TDMA. Then there's another one, CDMA. And those are both ways that we kind of communicate this different mobile stuff. But I'm going to leave that up to you. In terms of architecture, we can see that a mobile network has some pretty interesting architecture. Most of the devices, not most, pretty much all of the devices connect to the subscriber portion of the network. And then from that subscriber, I'm going to call it kind of hub, we then go from that hub to the base stations. And then those base stations take us back to the provider side, the backbone of the network, which we referred to earlier as the what's the word I'm looking for here? The data, the stuff that's important is happening here. So, and to get from one to the other, you have to have those base stations. Now, in real life, what does a base station look like? Well, of course, a base station would be a building with data centers and all that. But one place you can see the base stations is on the side of the road, and those very tall antennas that have the rectangular objects at the top, and they're pointed in every direction. Those are those base stations. And that's what you use to really get that mobile network out to the subscribers. Okay. And for the most part, they follow major roads or large uh, traffic areas. Okay. So that's mobile network. We are pretty close to the finish line. So we're just going to jump right to the next one in terms of different techniques for wireless security. Uh, you may have seen all of these acronyms at some point. Okay. These are different wireless acronyms that we use in terms of security. SSID is pretty much the network name. WEP, EAP, WPA are all different ways to encode passwords and password protect networks. Same thing with WPA2. And the first step to any good security system is going to be limiting access or access authentication. And you can make so many things more secure just by actually putting well thought out passwords that are not easily socially engineered. And when we're thinking about data systems, I think the IRS, someone used a socially engineered uh, password, something based on aspects of their life, and then someone retrieved that password and stole hundreds of thousands of individuals' information. And with a wireless network, this is even more easily accomplished because you don't have to be at the physical terminal inside of a secure location. You can do this, with a wireless device. So these levels of security, and these are definitely not all, but these kind of first five levels of security should always be engaged. It should be a behavior protocol to always avail yourself of these security options if you have them. Okay, and After security, we can see kind of a convergence of all these different things happening on these networks. And what things are we talking about? It's the things that are advertised to you when you sign up for a smartphone: voice, video, and data. And since we have these different layers, we are able to converge these different types of media in these wireless networks. And it's because we have technological innovation, it's because we have a market that demands this, and we have kind of a regulatory environment that makes sure that this stuff is done in a way that protects the consumers of this type of topology, or not topology, this type of service, and also provides a infrastructure that scales well. If we look at what we've covered today, we have really looked at the nuts and bolts of data communication systems. And what we have found is that if done properly, we can build on topologies, we can build on architectures, we can build on flexibility and different levels of client and server relationships. And using all that together, we can deliver integrated experiences, whether it be voice, video, or data. And that's exciting. The book also talks about this type of convergence with e-commerce and other consumer projects. I'm going to leave that up to you to read. But this is chapter 6